Okay, good morning. Let's get started with the discussion session. So Suresh and I will be sort of handling this. So this is what we thought. We will have a very quick, maybe 5 minutes or so for people to ask any quick follow-up questions on the previous session. Then we have two panelists, Alvin, Chua and Ajit Mehta, who have not spoken yet, and we will give them an opportunity to say something about some interesting problems that they find challenging, etc. And then we will come back to an open discussion. So first, we will have a few minutes for any follow-up questions from the previous session.
Yeah, my question is for Stephen. Here. Yeah, so I guess you were beginning to touch upon, the overfitting problem, right? Do you have any thoughts of what can be done to guard against it, so that we don't suffer from that when we look for these signals?
To deal with overfitting?
Yeah.
Well, if you have enough training data, then it's not a problem. If you have enough training data, then it's not a problem. So, when we train networks with like 10 million simulations, we don't see any overfitting. You can always check it because you can set aside part of your training set for validation. Excuse me. But I guess the problem is when you say want to train on really expensive simulations like population synthesis codes or something like this, and you can't generate tens of millions of examples. Yeah, it's a tough problem. There's approaches like say multi-fidelity training. So you could train say initially on a cheap model and then try to fine tune it on the expensive one. And then the hope is you don't need as many training examples in the second one. But I mean, in this fine tuning stage, but it's a hard problem to deal with. Yeah.
Hey, hi, Stephen. So one of the question is for you and another one for maybe Ajit and Tejasvi to answer. So let me start with question to you. So when you say simulation-based inference, right, you need to simulate things. So for real data in current scenario, right, where there are very few signals, you can use real data as actual simulations and train the network. But in future detectors, when that is not the case, then do you have any idea how you can tackle this with this approach?
I think you have to. There's various approaches, I guess. Like if you have some way of simulating your detector noise, then you can, then having a good simulator for your detector noise is the way to go. But if you have, say, with Lisa, maybe you have a bunch of sources visible at the same time. Again, then you have to just, well, one approach would be to simulate all of the signals that you're not interested in and ignore them when you're training. That would marginalize over them. But also, I suppose another approach would be you could take, say, real Lisa data with a bunch of signals in it, and then add a new signal on top of that. And that could be the signal that you look for in your training data. So I don't know. I haven't really thought about this a lot, but if you have, say, maybe you want to look for a massive black hole with a bunch of galactic binaries you don't care about, you could certainly simulate that kind of thing.
Okay, and another question is maybe to Ajit and Tejasvi. So Tejasvi, you glossed upon role of searches, right? So for next generation detectors, right, we will have so many signals which are loud and which are easy to detect, but then buried under them, like you mentioned, most of the signals will be low SNR. So what kind of role searches will play, or they have to change or go towards to improve this so that we can detect very low SNR signals which we can detect right now, even after having the foreground of very loud signals? And or does a role of search is not relevant and we can do really like global parameter estimation on the data, and is it possible realistically? Can you comment on that?
Yeah, so I think at a high level, there is no difference between search and parameter estimation. It's just like it's all the same thing. And it is just we are dividing it into stages. So if you could write down a thing where you want to fit for everything in the data at once, and I don't know, Steven gets really good at it, then there's no need for anything, I think. But yeah, this is like some idealized world. I don't know when and where we will, when we will get there. So, and if you ask me, like, if the data existed now, what would I do? I would sit down and think hard about it. I just haven't thought hard about it because the data is not here now. So I think that's an honest answer.
Ajit,
Maybe
do you have a take on that?
I mean, like, yeah, I mean, I think, yeah, for higher scenario events, maybe all those will act just as a confusion noise, right? So, but I don't know, there has been some work, like I haven't also personally thought, there has been some work by Alex Nietzsche, some people who say that depending on method, whatever you use, there could be sensitivity will loss up to 40%. So, but this was, I think, few years ago. I don't know. I mean, one should think there must be some. Though it looks complicated, but it should be solvable problem according to me. But let's see.
Can I make a comment on that?
I think Alvin wanted to make a comment, then you can come back. Yeah, Alvin, go ahead.
Okay, right. Yeah. So I just wanted to sort of follow up on basically what Teja was saying. So he's absolutely right? So if you look at it at a high level, in principle, from search all the way to inference, it's really the same sort of task. But then I think the key thing is that in practice, it's very difficult, right? And these difficulties get exacerbated for future detectors. And I was planning to elaborate on this. So for certain types of sources as well, it's even worse, right? Because there's actually now a third task, which is often sort of neglected, that happens between the detection stage and the inference stage, which is actually how do you get from the detection stage to the inference stage, right? How do you localize? And that could possibly require yet another way of thinking about things. Yeah. So I think the difficulties are just practical in nature. Yeah.
Your mic is not on, is it?
For the high SNR events, I think the low SNR ones will act as a confusion noise. And for the low SNR events, I think the residual of the high SNR events, that is the parameter estimation inaccuracy, can be the biggest problem because they can act as the residual can be stronger than the low SNR events. And I don't think global parameter estimation is going to work. I mean, this is to be, I mean, that is not, astronomers do it in general astronomy, right? Like radio astronomy, you use something like clean, slowly you remove one by one and so on. We know everything is together. Right now, the overlap is not there, which is why we don't worry about it. But I think this will organically get fixed as the detector sensitivities improve because people will see how to solve it slowly.
Something on this, Alvin?
Yeah, so I actually missed the context of what he was saying, but if he's talking about the LISA context, right, then you basically essentially you're right. There's a hierarchy of sources, right? So there you need to basically that's what the global fit is trying to address, right? So in this hierarchy, what are the correlations between the different source types? So what sources are safe to treat independently, as in you can remove and then work on the residuals, but which sources you have to do sort of globally, right, simultaneously. So these are all problems that are sort of they've been thought about quite some time really in the LISA context. Yeah.
But I think this will be relevant for the BNS context in the third generation detectors as well, right? Because the signals are going to be very long, and also the number expected is very large.
Possibly, yeah.
So, shall we take a last question from Patrick? Had a hand up, folks.
Okay, yeah, please.
So this is a question to Yam. So regarding the squeeze states introduction into the dark port. Now, normally without the squeeze state, the dark port entry was with a vacuum state. Now that the squeeze state is introduced, does the time resolution get affected by virtue of delta E, delta T uncertainty? Because now no longer the delta E is the delta E corresponding to the vacuum. So whether the time resolution of the detector gets affected by this. But probably this time resolution is much shorter than the photodiode, the photon counter detector. Probably that doesn't make a difference. I wanted an answer for him.
Yeah, I think the answer is no. There's no impact on time resolution. In the end, let me think about this. I've not really thought about this ever, but of course they're different. You know, because the delta T is extremely. Let me think about this. 1 second. Yeah, I think that's not even the correct way to think about this. I think this delta E times delta T in the uncertainty relation doesn't really play a role in our case, because the delta T in that relation is really corresponding to something like the period of the light. But that is, of course, these are very, very short time scales compared to any sampling that we are doing, which is like going up to thousands of hertz at most. So I think we are not even close to the regime where we care really about quantum uncertainties in time resolution.
Okay, so let's move on to the next aspect. So I believe Alvin has thought about some aspect that you want to bring up. Alvin, do you want to go up?
Oh, me first? Yeah, okay. Right, I guess, thank you. First of all, I just want to extend my thanks to you, Ajith, and the other organizers of the workshop. I'm sorry I couldn't be there, but as you well know, I had trouble with immigration, basically, which is silly, right? Because it's a really short flight for me. Yeah, so I guess wanted to, I guess the task was to sort of come up with some extra questions. So I decided to wait until the session was over and then sort of add on to anything that may have been missed. So I think in particular, my expertise and interests are mainly in the sort of stuff that Teja was talking about. So I think he did he did a really comprehensive sort of overview already. And it's also striking to me, right? Because he was speaking quite generally, but maybe the focus is a bit more on the ground-based detectors. But you can really see that we face a lot of the same problem in LISA as well. There's so much overlap in the problems. So yeah, so maybe the first point I wanted to bring up is that so there are maybe some a bit more technical things that Teja didn't cover, right? And really these are maybe a bit more distinctive for LISA. So the first is that basically when you're talking about the parameter space, right? The space of the possible signals, right? So when you have these future detectors, the information volume that's in this signal space is exponentially larger, right, than anything that we've coped with so far, right? Maybe the closest analog would be like continuous wave searches in ground-based, right? But those are also difficult for their own reasons. And for LISA, it's not just long signals with many cycles. We also have these signals can be very complex, right? They can be very strong field, and they can also have very high SNRs. So all of these, without going into the details, basically they sort of they may actually necessitate sort of a third way that we think about searching for signals. So previously we used template banks, right, for ground-based detectors to good effect. And then the thinking for LISA is that, okay, we will have to switch to a stochastic sort of type of search and basically just trying to sample the likelihood or something similar, right? But it's possible that maybe we have to explore alternatives like just optimization, stochastic optimization. So this is one thing that I think is one difficulty, right, that may arise. The second point is that so again, for LISA, certain types of LISA sources, they're going to be long-lived, right? They're sort of going to be there throughout the entire data stream, but they also exist in the strong field, right? Which means there are more degrees of freedom, and these come in very complex ways. So examples, of course, are extreme mass ratio in spirals, which is my own research interest, but also I think stellar origin black holes as well. They can be plagued by this problem. But the problem is that you have these signals, right? So they are complex, they're produced by complex dynamics, but the problem is they still look fairly simple, right? In the sense that they may be dominated by one or two strong frequency modes. right? And this gives rise to this thing called non-local degeneracies, right? So not the usual degeneracies in parameter space that we are talking about, but non-local in the sense that these signals, you can match them well with many, many templates that are sort of far away, very far away in parameter space. And that could also mean that basically, if you're doing a search, right, your first, your search algorithms may find some answer, but that answer may not be enough to get you, to jump in and do an MCMC locally, right? So there is a sort of a middle step which needs to be thought about. Yeah, so that is what I wanted to add. And then, as Teja mentioned, I think this was also a question, right? So someone brought up that, eventually you're going to have these high SNR sources, and that's where model errors become important, right? And these model errors can actually exceed the statistical error due to noise. So I think other than approaching it from the modeling end, I think on the data analysis end, we need to actually study better. I think more effort needs to be made to study how these systematics affect analysis and also come up with more methods. So there are already methods, right? People are looking ahead, but I think more is required. Yeah. That's all I had to say. Thanks.
Okay, thank you, Alvin. I just wanted to make a comment. So these non-local correlations are certainly an interesting part. I thought these are an issue for the searches for continuous waves using ground-based detectors as well. And there are techniques developed to address some aspect of it.
I think so, but I think it's not quite as bad because there are parameters. It's a simpler parameter set, right? The signals are truly simple, right? Whereas in these types of signals, they look simple, but they're actually described by complex dynamics. So you're sort of like over describing the system in some sense. So I think so you're right, they do exist already. I'm not actually too familiar with the techniques or if there's any literature that specifically addresses how to cope with them, but I think they're just going to be worse for these types of sources. Yeah.
I see. Thank you. Anyone else want to follow up on these aspects? And what? So is the community just starting to address these questions now in the LISA data analysis, or there are already some directions that you're pursuing?
Yeah, good question. I would say not really, but in the sense that, especially for example, the systematics questions. This was really, we I think in a famous paper by Kurt Cutler and Michele Vallisneri, this was back in 2007, right? So 18 years ago, they were already sort of thinking about this. I think it's just the fact that, that there isn't enough activity, right? So, but people are thinking about it. There have been papers coming out, but I think this problem is getting more important, and especially now with ground-based 3G detectors coming on, they're going to face something similar as well. Maybe not as extreme, but that could also mean it's a good setting for us to actually develop methods and test them. That's my opinion.
Yeah, okay. This aspect, we did have some discussion in the source modeling session as well earlier this week. Okay.
Hi, Alvin, could you describe the current status of the LISA global fits? Like what is going on with that?
So right now, I think activities are sort of ramping up significantly, right? Because after the official adoption of the mission by ESA, and the consortium has been restructured as well. So I think the formal activities are really coming together, and of course these problems, people are looking at them more in a more organized way. But I think there's also people have also been doing work on the global fit problem sort of individually, right? So for example, Neil Cornish, he's been working on the galactic binary and massive black hole interplay for a very long time already. So I think currently the status is, so we're putting it all together, right? And then the task is to sort of develop a pipeline that can cope with this. But I think it's a massive task. So it's not clear to me personally anyway, right? So whether it will be more productive for me, myself, to actually work within the framework of this formal organization, right, with specific tasks that they and deliverables, or whether it's more possible to make progress as individual researchers. But that's just my personal take on things. But yeah, in terms of status, things are ramping up essentially.
My question is to Professor John. You have discussed about the different kind of noises, intrinsic noises and the vacuum noises, where you talk about vacuum fluctuations. One thing is this vacuum leak, how it affects the sensitivity, and is there some calibration data for that? You talk about vacuum fluctuation. One thing is this leak rate, global leak rates, which you cannot avoid. So is there any calibration data regarding sensitivity of the detector and this leak rate?
Vacuum leak. Yes.
So if you mean that vacuum can also, the fields that enter can also leave, and in a way that you cannot control, losses, for example, because otherwise, so I mean, the only bad thing that happens to us is what also Rob said. Essentially, we send something in a well-prepared state, and then it can couple with open ports. Whenever there's loss, there's also an input for coherent vacuum. And so it doesn't really matter even what mechanism there is that leads to this coupling. It can, there's always an input port for coherent vacuum. And so then you get mixed states with like one squeeze state that you send in, and then you mix it with all the coherent states that come in from all the open ports. And then you measure that mixed state at your photodetector, and then you get degrading of squeezing. That is the main thing that we are worried about. And so, yeah, and that is automatic. So whenever you have something exiting, like the transmission of your end mirrors, for example, that's an open port. Losses anywhere in the materials are open ports. So all of this will create a big mixed states of many coherent fields plus the squeezed vacuum that you send in. And that unfortunately is at the moment the main limitation to what we can do. And so we have to first understand all of the loss mechanisms and then come up with ideas what to do about it.
So I also have a question for you. So you mentioned during your talk that there is a improved sensitivity at low frequency by using these AI ML techniques, right? On the servo part. So now the question is where does this improvement gets limited? Because in principle, when filters were used, so there is always some limitation which order filter you use, and in principle, if you are using linear filter, okay, then there is direct limitation. So if you use these AI-based techniques, this improvement should be limited by something. Is it only by the learning of the algorithms, or what other factors are taking place?
So we do not yet know really the limitations of the machine learning, but I can say a few things. So at the frequencies where you really need to control the system, where you actually want to learn something about the system, about the state, and use it to feedback and reduce vibrations, there your controller is ideally linear, because the point is that your machine is linear. And so when you want to regulate a linear machine, the best way to do it is with a linear actuator. The reason why machine learning can help is only because at some frequencies you don't have to control, but you inject noise. And so that is where you can gain. And we don't know really what is the fundamental limitation. What we have seen in our implementation is that it is really a non-stationary kind of thing what happens, because essentially when you send in the glitch into the neural network, it doesn't come out. Or if you send in stationary noise, glitches come out. So there's something weird happening, and what I suspect at the moment is, for example, that it takes in the stationary noise from the sensor, and it kind of converts it into weak glitches that are distributed over many frequencies. And so it redistributes the energy over a wide band of frequencies. And I think fundamentally what I can imagine is that the fundamental limit is probably the complete thermalization of energy in a certain band. That means, like, essentially you take energy in a band where you want to avoid noise, and you completely thermalize it, as which means essentially making it as broadband as possible, the redistribution of your energy. And that is your fundamental limit. But we are far away from that. So I think for now we are talking more about practical limitations, about improving your simulation, because you have to represent the true system in your simulation. And I think that is where our current limitations really come from, like how accurately we simulate data, how accurately we represent the dynamics of the detector, and so on and so forth. I think this will keep us busy for forever before we actually run against fundamental limitations.
So I have another question, if I may ask.
Can I also respond to your question, the first question? Yeah, we have always had this issue when we were trying to extract information from sensors, which is the amount of coherence find between any two given sensors. So I believe when the signal to noise ratio in a given, like even to build a machine learning algorithm, we need to have information. If the information, as you said, is lost in the thermalization of the signal, then we cannot do any better. So I think the fundamental limitation will be the signal to noise ratio of the sensor for the parameters that we are interested in.
Yeah, absolutely. So for the frequencies where we actually need to control, then of course, at the moment we are not sensor noise limited typically, in some cases even so already. But yeah, that will be, but in any case, typically we are already robust enough. So the performance of the control is typically good enough to operate the interferometer at a high sensitive state, except for the noise injection, which is currently limiting us. Of course, at some point, we would probably like to even improve the robustness of the system, and then we need better sensors at some point as well.
So I have one more question. I may. Okay. So this might be some stupid question, but I will nevertheless ask. So as you mentioned, like in squeezing, the main problem comes with this losses, right? Because the quantum state is getting lost, and like the quantum advantage is going away. Isn't it possible to use some other kind of correlations? For example, maybe squeeze light is there, but like somehow use some entangled photon sources and do some heralded measurement where these noises can be overcome, or has it been discussed? Or because I'm not from this community, I have joined recently, but I would like to know.
So that's okay. I can give a concrete example where we also thought about something connected to this. So this is about these filter cavities, which are these long things that we need to align our ellipses, which are really tricky because they typically introduce a lot of loss, or we have to make them very long so that these losses matter a little bit less. For some of the detectors that we plan in the future, it really gets prohibitive, where the filter cavities have to be like 5 kilometers long or so that we have the correct performance. So then it was thought that, okay, you can actually use what we call EPR squeezing, where you explicitly use entanglement before. I haven't shown a diagram, but it's a publication that we made some years ago, where essentially you can substitute the filter cavity by using the interferometer itself as a filter, but then you have to split the entangled photons by some megahertz, and you send them all into the interferometer, and then the interferometer does something to them, and then you exploit at the very end the entanglement between the photons to align the ellipses. It's a little bit, yeah, without schematic. I can point to you to the publication, because that will explain it to you. But yeah, there are some tricks you can play to, in some sense, reduce loss, but there's also penalties. So we haven't really switched to these exotic schemes yet, because they come with some trade-off, and we don't really know at the moment what is the better option. I can say for Virgo that both streets are developed. There's the main thing, as I've explained it in my talk, and then there's the EPR squeezing, which is developed in parallel. And maybe it will be swapped if we encounter some problems with the filter cavities. So in any case, I will share I will also maybe in the shared document, I can put the reference so that other people can have it.
Okay. This is a question for regarding binary neutron star mergers and machine learning. So yesterday we have seen that the phase space available for the equation of state for neutron stars are huge with present detection of NICER and all those things. The question is, when we have the future detectors, means we are trying to detect the last few cycles and the post-merger remnant of the binary neutron star mergers, the simulations are very expensive. How does the machine learning will handle them? Because you can ask Kenta and all those things, simulations are hugely expensive. We will not have millions of simulations. So how does you plan to handle those things? Because post-mergers, you are talking about post-merger signals from binary mergers and all those things.
Well, I didn't make any claims about being able to do that, but I mean, yeah, I don't really have an answer. Maybe you can try to parameterize your equation of state in a way that might be, somewhat flexible, and you try to infer that. I don't really have an answer for you.
The phase space is huge, means even for classes of equation of state, you cannot have a simple parameterization for that. You can, we have discussed this yesterday. It is really means, what I am trying to ask is, if we don't have millions of simulations, so what about if we have thousands? And is there any schemes that of algorithms we are trying to develop so that less training data can have a better output for the machine learning? That we have gone from neural network to transformers, right? They have performed better. So is there any work on those lines?
I mean, we're trying to improve the simulation efficiency and overall. I mean, it's the same problem that happens with, say, population simulations when you don't have that many simulations. The only approaches I can think of are, say, training on a cheap simulation and then trying to fine tune it. But I agree it's difficult when you have different, sets of parameters that you might want to deal with in a large dimensional space. I don't have a good answer for you. It's one of my problems for the future.
I understand. I was just asking, is anyone working on the algorithm thing towards this machine learning in your groups or in this?
There's a general goal within, I guess, the SBI community to try to improve the simulation efficiency of the algorithms, but I don't know how successful it is so far, but people are making progress.
Thanks.
I don't know, Ajit want to add something? Because there is another aspect of waveform modeling, right? He's trying to solve the inference problem. There are probably also ways of creating semi-analytic waveform models, which you could have from physics inspired way of parameterizing things.
No, I think that's what, like, simulation-based inference requires like simulations, of course, but if I understood your questions, it's what more about waveform modeling. If you're given in a limited number of the actual simulation of the physics, and if you can come up with certain parameterization that can give me millions, and that from there he basically pick ups, right? I mean, this is how I understood.
Yeah, you can model. Yeah, try to model the forward model in an easier way.
I want to follow up on this, but if, for example, the number of training that you need to do is larger than the number of analysis that you want to do, then always your cost will dominate by the training part, right?
Yeah, I mean, that was kind of the last point I was trying to make on my slide, is that, how do you leverage all, this training across simulation, across, different analyses more easily. It might be something like, making somehow more flexible networks that have been trained a lot and then can be quickly adapted, so sort of foundation model type things. But nobody's really worked on that a lot yet.
So currently, can you give us a sense of the current status? For example, you presented this work on eccentric analysis on the LIGO Virgo Agra events. And you also mentioned that was trained on the eccentric SUBNR waveform model. So what was the inference was extremely very fast, but what was the time required for the training using these models?
I think it was pretty standard, about a week. That's what we usually train when.
With a few hundred cores? Or?
No, with a GPU.
Ah, one GPU.
Yeah. And maybe 100 cores or something.
Yeah, so I just wanted to add one thing that because in this neutron star merger signals, the in-spiral phase is very long, and only in the post-merger, the last 5 seconds, maybe the problem where we don't know, which would really a lot depend upon the equation of state and internal composition, temperature, conditions, and all that. But we have a fairly good idea of what would happen up to the very last stage. So the analytical models that are available that can be used to train, infer, search, and parameter estimation. Maybe only the last bit of some part we may not be able to, but I think we have fairly reasonable models available to search for a 1 hour long signals even in the next generation.
Stephen, this is a question for you. Very recently, I forgot the name, but I was listening to this talk by someone on inference, where they were trying to use different models while doing the parameter estimation with Bilby. Is that also something that you plan to do with Dingo, as in like you don't train it with one model, but multiple models so that it also picks the best one?
Yeah, that's something that can be done pretty straightforwardly. I think there was a paper by Vivian Raymond and a student possibly doing something like that, where I think they trained on 2 models at once and then performed inference. And I think what they found was if they injected one of those models, it kind of recovered the posterior that you would have expected for that model, essentially. I mean, if there's a big enough difference between the waveform models. Yeah, that you can essentially marginalize. It's a way of marginalizing over your uncertainty in your waveform model.
Hello, here. So this is again a question about this training that you said that the cost is too high. Can we have a like online database of these trained machines?
Yeah, we have one. It's on Zenodo, and we'll try to keep it updated with newer trained models. Yeah.
Okay, thanks.
But I just to add, I mean, I think what you can do with these trained models is like take pieces of them if you want and try to retrain that for your own application, you know, aside from just using them correctly.
Hello. My question is from these challenges of data analysis talk, where they have discussed about the moderately complex problem. So I was just wondering how we tackle these data gaps in the long signals.
Data gaps in the longer signal, how to deal with the data gaps?
How to deal with them?
Why there are gaps and how we tackle it.
Okay, why there are gaps and how to deal with it? Was that the question? I mean, I'm not an expert on LEAP or anything, but I think there's gaps because satellites have to kind of reorient themselves sometimes. Maybe else wants to add.
Sorry, what was the question? And I think it was for Teja, right, actually. But was the question why there are gaps in future gravitational wave data?
Yes, why there are gaps in the long
Why there are
signals.
gaps? So I can answer for Lisa, and maybe Teja can talk about the ground base. But for Lisa, there are going to be all sorts of gaps, right? In fact, there are going to be planned gaps, right? So Lisa, even though the mission is going to last like 4 years, the duty cycles is estimated, you know, at most 75%. So really, you have 3 years of data. So there, you need to take the, you know, basically the satellites offline. You need to repoint them fairly regularly as well. So these are the planned gaps. And then, of course, you know, there are unplanned gaps as well. These, you know, nobody can predict. But yeah.
Yeah. My question is to Ian about the site surveys. See, when we go deeper, like 100 meters or so, then the seismic vibrations go down. But then you go from one site to another site, then also there is fluctuations. So how is the trade-off? Like if you go to another site, which is more suitable and go a little more deep, would it be can it compensate for the, for other inconveniences?
It depends. I mean, there's really so much variety between sites. There are sites in Australia which are as good at the surface as any site underground. So it really depends. If you are used to like the Virgo LIGO level of vibrations, then going a little bit underground is giving you a lot. One should, however, I should add something. In LIGO and Virgo, when you look, in the band in the observational band, the main noise is actually produced by the sites. So one has to keep in mind that a lot of that noise would go away if you move the machines, pumps or whatever away or put them on dampers. Of course, you might also know, for example, at the Livingston site, during some months in the summer, there's like the logging operations, which add also at a slightly lower frequency some noise. So, but let's say these things you can anyway easily avoid. Then there are hard things. For example, at the EMR site, I'm not sure exactly. So, for example, one of the ET Cannon sites, the surface vibrations are quite loud. I'm not exactly sure what is producing them, but these might be, for example, wind farms potentially, but I'm not sure. It is also connected to the geology because it's a soft soil. Then, of course, anything that is producing vibrations produces a lot of vibrations in terms of amplitude. But if you are, I always think, this is for things like ET. It is not only about what you find today. It is also about making sure that the site quality, as you find it today, will be preserved for 50 years. And now that is very hard at the surface, and it is much easier underground. So one should also think about that. And this is a very important topic for ET as well.
100-meter decided, meaning it could be 200 also, right? Then you have even
Yeah, no, this is entirely at the moment decided. So at Sardinia, I can tell you it is completely decided based on the atmospheric Newtonian noise. So essentially acoustic fields, temperature fields that are moving around. We predict the Newtonian noise as a function of depth, and then we set the detector depths at 250 at the moment to be safe. Maybe already 150 would be enough, but it's our models are not 100% reliable at the moment, so we have to make some margin. For EMR, it is a combination of atmosphere and then also seismic fields, but EMR has a very quick reduction of seismic vibrations because the big vibrations are always in the soft surface layer. And then when the harder rock comes, it is like declining very, very quickly. And so also there, the seismic noise we don't have like continuous measurements across depth. But one could expect that maybe already at 150 meters or so, that even the EMR site has very low vibrations already. It's a bit that. But I think ultimately we really want to just avoid atmospheric Newtonian noise because we wouldn't be able to cancel it out. While seismic Newtonian noise, if you have some limitation, you could still think to make a Newtonian noise cancellation system.
Hi, so this is a question about Dingo. Dingo operates on strain data where you a priori assume that there is a signal, right? So my first question is like, how is its performance when there is no signal, just noise? There was in your paper you mentioned that you want to build an early warning kind of system where you will first detect that there is a signal and then apply parameter estimation. So that stuff. And another stuff is in your paper you talked about going around not using a PSD. So knowing PSD requires certain chunk of data, and you don't want to use PSD, I think. So in this direction, is there any step?
So the first question was, what happens if there's no signal? Yeah, well, if you have a far enough prior, then you can effectively have no signal sometimes, right? If you train it, I mean, it depends on whether or not it's seen data with no signal in it during training. And we don't explicitly do this, but if you have very low SNR signals that might be included in your prior, then effectively you see that. I haven't analyzed no signal exactly, but in principle, you could just include no signal in your data. And the second question was maybe more about kind of on-source noise estimation. I think you probably always want to whiten your data because otherwise you can have sort of outlier inputs to your network. But you can do this somewhat imperfectly and use, say, a PSD that's off source, but still use kind of real noise. I think that would be fine.
So can you add like batch norm stuff, layers in your neural network model, which will learn PSD as well while in training?
Yeah, I mean, you can in principle train on real noise and have it try to characterize the noise spectrum to some degree. I mean, I'd have to think, maybe we could talk later about technicalities like that.
Then again, you don't, to begin with the observing run, you don't have the real data. So learning actual PSD.
Well, no, for that, you can like say have synthetic PSDs that, you know, you can simulate. And as long as you cover your sort of distribution reasonably well, you're fine.
But sometimes they are too optimistic, PSDs.
Well, you try to be, I mean, try to get it as accurately as possible. Yeah.
Yeah, thank you.
So my question is to Stephen. It is on the lines of Aditya's question. So for example, suppose you have two effects that mimic each other and you have trained on both of them simultaneously. So what is the output going to be? So for example, in traditional PE, what we do is we perform PE on both of these effects, and then you compare base factors, and then you can basically know which one is preferred. But in Dingo, if suppose you have trained on both of them together, then what is it going to pick?
I couldn't quite understand. There's a bit of echo maybe. Could you try to say that slower or something?
Okay, so my question is on the lines of what Aditya was saying, that suppose there is a scenario where you are training on two waveforms which has two different effects, but these effects can mimic each other. Now, given that you have trained on both of them, so if your data has one of these effects, what is Dingo going to pick? So for example, if we are doing traditional PE, what we will do is that you will perform PE on both of them, and then you compare various factors, then you know which one is preferred. So my question is basically, how is it going to differentiate between these?
Yeah, it's going to see which one it can fit better. I think what would happen is probably it would weight the two posteriors by the base factor between them. That's what I think would happen. I think that's what Vivian saw also in their analysis.
I think multiple things, I think you said. So let's say if you have a GR signal and you are trying to infer it using different waveform models or different features added on the waveform model, maybe microlensing. Okay, so I guess now questions are clear. I guess like for the GR model, since we have various like, you know, kind of there. So then you just do like, you know, you can train in simultaneously, but for that, like
having like a beyond GR wave.
Beyond GR or microlensing or whatsoever.
Yeah, well, the difficulty there, I guess, is that you have different parameter spaces. So you'd have to rig up some way of trying to get, you know, optional some extra parameters or yeah, I'm not exactly, you know, well, I suppose your GR waveform could set those parameters to 0, and then it wouldn't be a problem, right? You just do the inference in the larger space. Yeah, I haven't thought about that, but you could come up with something.
I want to bounce back to Jan and the question of site selection for the Einstein telescope. My understanding is that it's mostly a political decision or a political discussion now, but if we take this aside, I'm curious. I mean, what are the main physical aspects that would drive ultimately the site selection? Again, I understand most of it is political, but physically, what needs to be done now to make an ultimate decision?
So, assuming that we scientists have like the full power to drive that decision, I think we should in any case be concerned about the site quality in two aspects, like in terms of construction, because it's really if there are certain risks, we have seen in Kagra that things can go badly. So one has to be aware of that, and it affects the detector operation in a very significant way, and it causes problems. So one has to be aware of that part, which has nothing to do with the geophysical environment, but more about the geology and underground water and things like that. So that is the one aspect that I think probably will, from the technical perspective, probably be the main aspect of site selection, in that class of arguments. And then, of course, I think in the end, the seismic spectrum that we observe underground is then the next thing that matters from our perspective, like politics aside. And then I think when it comes to magnetic fields, they are kind of the same everywhere in the world. So there's no other geophysical parameter anymore that could really make a big difference for site selection. So I think it will be geology, seismic spectra, and that's basically it.
Are they being measured at the moment or in the next year or so?
Yes, so we have borehole measurements at all sites at this point. I think we should have more because there's also a little bit of variation, across the region. So one has to check and make sure that that there are no outliers and stuff like that. But yeah, this is all being characterized, and I think quite in detail at the sites. Yes.
Thank you.
Okay, in the last few minutes, Ajit, I understand, wants to bring up another challenge in the future detectors.
Hello, I think this has already come up during various subsections submitting. So, so during ET or the 3G detector era, so I mean, as Ms. had pointed out, so there could be some. No, I'm not sorry. I'm not pointing the slides. I'm just saying. So there could be some events with, I think, around 1,000 SNR or something. So at that level, though I haven't done zero level calculation, I guess we will need very precise, of course, waveform model whatsoever, but detector calibration uncertainty, right? If you're really interested in testing GR, I don't know how much it will matter for slide. If there is slight problem in our like astrophysical, uncertainty like mass parameter, etc. But if you're really interested in precise test of gravity, I guess how much accurate we need to be, right, in terms of detection calibration.
Yeah, I mean, we are aiming for calibration systems that allow us to retrieve all the information from the data, limited by statistical errors. But that of course means 0.1% calibration errors or better. That is really tough. That's one of the really hard problems. And we do already start to develop new types of calibrators, Newtonian, we call them Newtonian calibrators. There might be, so essentially, just to explain, the idea here is that you have some moving masses nearby the test masses, and then you predict the gravitational force fluctuations on the test mass, and then you retrieve calibration. So there are also tricky parts about that mechanism, even though it seems very clean, but of course the details are always a little bit difficult. There have also been a couple of other proposals. I personally think that the Newtonian calibrators may be the only chance we have to get to 0.1%. And then, yeah, it is really so good that we already started to make them now, because I think it will really take a decade or more to get them to the performance we need to understand all the
Say than 1,000 hertz?
Huh?
You can have kilohertz sort of vibrations?
No, we don't. The tricky part is the low frequency part. The high frequency part you can typically calibrate quite well because you know your setup, so the high frequency response is typically easier. But in the low frequency band where you have controls and all the messy stuff happening, there you want to have something more sophisticated.
Of course, the dream is that you get an astrophysical source that you can use to calibrate your detector, right?
Yeah, if you
Reality.
can, yeah, but then you have to know everything to 0.1%.
Perhaps with that hopeful expectation, we'll conclude the session. Let's thank all the panelists and all the speakers for this wonderful session.